Okay, good morning everyone. Today we are going to see the new topic in principles of compiler design, that is top-down parsing. We're going to see today what is top-down parsing and what is the recursive distant parsing. We're going to see two parsers in the top-down parsing. One is the recursive distant parsing, another one is predictive parsing. So today I just want to elaborate what is recursive distant parsing and then some of the derivations, how this works, the derivation and all these we are going to see today now. Okay, so we'll move on to the lecture now. Parenthesis taken, snap talk is over. Then the today's agenda is this, that is what we have seen in the past class, the recapping the previous hours. That is, we have discussed about the context-free grammar, how to write a grammar. All this we have seen. After that, the grammar, the context-free grammar, how we are making a grammar for a specific statement or a specific programming language. As you all know that we know that you have to recall back about the context-free grammar. A grammar can define a complete syntax of the programming language that could be done, and then you should know the difference between that context-free grammar as well as the regular expression. Now we will move on to the what is the today's topic, that is top-down parsing, that is recursive distant parsing. That's what we're going to see today. I will see then we have review questions in this chapter. Then what is next? What is going to be the next lesson? What you're going to learn it? That's what we're going to see now today. Okay, guys, fine. Now we'll move on. What is top-down parsing? Top-down, in the sense, we can understand that what top-down is, from top to bottom. Okay, top-down. You consider any object or anything which already we have learned it from the childhood or any classes in between. We have learned about what is top and what is down. So top is always in the top. Okay, it's what is in the up or where we are starting up. That is the top down parsing. So considering the tree, here we're going to build a parse tree. It is going to be a tree. So considering a tree, here the top is the root, just ups and down. Okay, it's not like the typical tree, the root will be down, the leaves will be in the top, but just opposite of here in data structure, the tree, the root will be the top and the leaves will be in the down. Okay, so the top-down parsing is a construction of parse tree by starting at the start symbol and guessing. It's all about guessing which is going to be the next branch or which is going to be the next input symbol. According to the next input symbol or according to the input word, we are going to derive that each derivation until we reach the string that is matched with the input string, that matches the input. Okay, so that is the top down parsing. Mm, then we'll see, I'll elaborate it a little more what is that. But actually the top down parsing or any parsing in compiler design, it constructs the parse tree. Okay guys, now what is top down parsing? The top down parsing, again, the parsing can be viewed as an attempt to find a leftmost derivation for an input string. So then you should know what is the leftmost derivation. Then you should know what is rightmost derivation also. Okay. So the parse tree starts from the root and creating the nodes of the parse tree in the pre-order traversal. As you all know that there is a tree traversing method, that is pre-order traversal, in order, pre-order, post-order. In the pre-order, I just want to tell you that suppose if we have an expression, so that is infix, prefix, postfix, okay, in the same way, when we have a tree like this, okay, consider a tree here, A is a tree, I mean the root A is a root, and then the B is the left subtree, and then the C is the right subtree. Suppose, consider this example as a tree. So the pre-order in the sense, the root will be first. Okay, the first is the root. Then what is the root here? A is the root. Okay, then left subtree. The left subtree we used to say that LST. Okay, so LST means here it is B. Then the RST. So RST in the sense it is the right subtree. So that is we got it C. So the final result of the pre-order of this example is A, B, C. So So this is the output for the pre-array traversal. So like this, you just consider now, you look at the tree here. So where we have started, actually, we have started with that root. Okay, the root to leaves, root to leaves. So this technique is called that is the top-down parsing, as well as we will going to do that the leftmost derivation. So this is what we're going to do it with an example today's class. Okay, guys. I hope you understand this. If you have any doubts, you can ask me any clarification on this. If you have any doubts, you can ask me. Equivalently, it can be viewed as attempt to construct the parse tree rooted at the start symbol of grammar for the input stream. So in the sense, we can view it as an attempt. We are constructing the parse tree from the rooted, that is the start symbol of the grammar, according to the given input stream. So the input stream can be anything. A program or the source code could be anything, like, it is the valid statement can be in the input stream. But the thing is, consider a scanf statement. A single scanf statement can have a single input, or at the same time multiple input. At the same time, we can have it a different type of input also can be done it in a scanf statement. Okay, as you all know that only the control string controls it in C language, especially I'm talking about the C language. The scanf statement works in different manner. We have the syntax can be used in different types, different varieties, or different types of input statement could be used. It, but the syntax is the same. For a single syntax, we can have multiple or the different type of statements, like, we can get input alone, we can get input only the integer, or we can get input floating type, and then we can get it the character type. Like this we can have it as we like. Okay, guys. So that's what you just consider as not only the scanf statement, even the printf output statement also can be done it in that manner. Okay, so here we should consider here that we have to start with the start symbol always. Okay, we have to elaborate the start symbol till to reach the actual input stream, that is the typical written source code. Okay, so next, the top-down parsers built the parse tree from the top, that is, I told you before this, top means that is root, and then the bottom means that is leaves. Okay, so top-down parsers build parse trees from the top, that is root, and to the bottom, that is leaves. Okay, guys, I hope you understand this. If you have any doubts, you can ask me too. Okay, so let me erase this. The next point is the parsers that use top-down parsing are recursive descent parser, and then LL parser. LL in the sense left to right, left to most to derivation. LL parser. Then we have it here. That's what we're going to see today. We will see at least one of the parsers now. Okay. So the example for the top-down parsing. Look at the grammar here. The S is a start symbol, and CAT. Then the A derives AB or A. Okay, consider the input symbol here. Consider the input symbol over here. Let me take it sketch or the pen. This S gives the is elaborated, or it is at the alternates, or it can be substituted by the right hand side, which means it is a grammar rules, or the rule of grammar, or the production rules, we can say. So this, we have only two production rules in this grammar. So yes, producing the small c, capital A, small d, then the capital A produces, because this A must produce the terminals at least. So we have that another production rule, that is A derives, or A in givings, or A is elaborate, or A gives the terminals, um, or it can be, we can say this alternates. So the correct word for the grammar is alternate. The A can produce the symbol, that is AB, either AB or A. Okay, either AB, A. Here the S must produce CAD. here the S must produce CAD, the A is a capital. So here you should know guys what are the symbols are terminals and what are the symbols are non-terminal. If you don't know about the grammar or the grammar symbols properly, you have to recall back and go through once again writing the grammar and what are the symbols are there, the terminals and non-terminals especially you should know. So I just want you to recall back what are the writing in writing a grammar we have four tuples or tuples or tuples, you can pronounce as you like. So S is the start symbol, as you well know that. If there is no start symbol, you can also add it with the first or the very first grammar can be added with the S is the start symbol. And then the production rules, productions, start symbol, productions, then the terminals and non-terminals. The terminals are the basic symbols. Sorry, then yeah, of course, terminals are the basic symbols, especially in the small letters, or the terminals are directly connect with that the source code. Okay, or the input word. Look at here, the CAD is the input word. Consider this is the source code or the word what we have written in the language. So what we are going to do it here, whether this word is acceptable by this grammar or not, whether this grammar is capable of producing this word or whether this word is acceptable by this grammar. That's what we're going to see it now. So how do you do this? That's what I'm going to elaborate it a little more for you guys. You can easily understand that now how that the tableau parsing is working. Okay, so consider that input word that is W, the input word W is equal to CAD. And then the grammar productions, you all clear about this? What are the terminals and what are the non-terminals here? You should know before going into the example or the demonstration, you should know what are the terminals and what are the symbols are non-terminals. Okay, I hope you understand what I'm trying to say. Fine. So now the S can be replaced by the CAD. The capital A is a non-terminal and then small CD are the terminals. In this A, I mean the second production rule, A is a non-terminal. This non-terminal producing it AB or A. Okay, AB or A. So the AB is one alternate and then A is another alternate. Here the alternate is a proper meaning you should understand that the A can produce either AB or A. That is why we are called it as the alternate. This symbol denotes or represents the alternates, which means at the same time the A cannot produce both of the symbols. Either any one of the symbols can be produced by the non-terminal capital A. Okay, now we will see the example so that you can understand easily, guys. We'll see this now. Okay, consider the start symbol starts with A, and then the start symbol gives that the input. I mean, it elaborates or it produces it. That's why it is called production. So S produces CAD. That's what we have written like this. Okay, then actually what A producing it here, but the S producing CAD, then A producing AB or A. Okay, so you can take a look at this here. So how do we consider, but the input symbol, look at that input symbol, as we are human being, we can directly match with our eyes. We can look at it, look into that, whether is it possible to, yes, of course it's possible. How do we possible? First we can take this C, and then instead of this A, the second alternative, if we take it, the second alternate, then we can get that, the matching input word, what is that in example is given. Okay, this is possible actually. Um, Next, we will move on. Consider this. The another when we have that the second alternates. The first alternate does not match with the input symbol, but the second alternate it is matching with the input symbol. Look at this. The first is C, the left hand side, and then the in the middle we have A, and then the right hand side we have C. Sorry, D. So the yes, the start symbol can produce, or this grammar is capable of producing that input word that is matches with CAD. So now you could understand that the previous slides, what we supposed to do with the parsing techniques. So whatever the program is given or the source code is written by the coder or by the programmer, that code must be matched with the compiler. So the compiler, the top-down parsing technique, the parsing is the main feature that is used to match, or the syntax should be matched with that the given source code or this even any high-level language. So this is how every statement is comparing and matching. Then the syntax is being identified. If there is not matched, then the error will be displayed on the screen. So that is also the compiler's job. Okay. But most of the times we think that we thought, even many students thought like, the compiler's actual job is to detect errors and display the errors on the screen. But actually it is not. It is just reverse in that case. Because whenever the compiler converting the source code into machine code, if there is any issue, if there is any problem, or if the compiler cannot recognize that the input word, that time alone it will show that it couldn't complete the process. That's why it shows an error. It shows error on the screen. Okay. Okay, I hope you understand this. We'll move on to the next one. So look at this, the problems with the top-down parsing. There are some problems here. One is the two problem. One is the left regression. Another one is the backtracking. So most of the games, the puzzles games and all, we used to have it in backtracking. Okay, we can start from the end to top. That is also can be done it, but sometimes we may not reach the desired input words. Sometimes we may not reach that. Consider the for loop is having 10 inner for loops like that, or the inner statement, or else if statement is having more than 10 else if statements continuously, if else, if else, if else, if else, if else, inside that inner if else. So the compiler might have confused in that. So let us see that what is the left regression and what is backtracking. That's what we're going to see it now. So what is left regression? Left regression, as we all know that what is regression? Regression is known as it's called itself. The regression, we know that it calls itself. Okay. So what is left regression in the sense? A grammar G is said to be a left regressive when it is when it has or if it has a non-terminal a such that there is a derivation. From the example, you can understand easily. So sometimes you may feel like it is a little complicated here. Look at here, the A is a non-terminal that produces A alpha. So the A non-terminal producing the production rule, that is A alpha. For some alpha, the A, look at here, for some alpha in the sense, here you have to recall back that the symbols. So alpha is a special grammar symbols that could be a terminal as well as non-terminal. It can be according to this derivation or according to the input symbols, we can replace it as we like. Okay, so here that look at here that A left recursive grammar. Yes, of course, this is the left recursive grammar. You know why? Sometimes when we do this left recursion here, we may not able to reach the desired input string even if it does support. If the grammar does support to produce a specific input word, it may not be reached to the destination or the given or the matching input string. I'll tell you how it is. The left recursive grammar can be caused a top-down parser to go to the into an infinite loop. Think about it. If a grammar is producing the infinite looping statement, then we could not reach the final destination or the final input symbols or the statement what exactly what they have given in the source code. So how does work actually the left regression? You can see this now. The next slide, it is easy. You can understand here what is the backtracking and what is the left regressive is a problem here. So the top-down backtracking passes can have affected the language accepted more inner loops. As I said before, so the more inner loops having that, for example, if a for one, you consider this is the outer for one, so I could not write it properly in this mouse, so please consider this is a for one. So inside the for one, if we have another for, so we have multiple for loop, so always the inner for loop is completed once, then the outer for loop you have to repeat it. Sorry, the inner for loop will be repeated whenever that for loop outer for loop is calling till the condition is true in the outer for loop. The same thing. So the for loop is going back here, the for loop 1 and for loop 2 and for loop 3 like this. So now that innermost for loop must be finished. Okay. Then it has to go back to this for loop here to back to this condition. If it is true, then again this loop will be continued. Okay, this loop will be continued. Okay, so that's why we are calling it as the looping statement. Then when this loop is completed, then it has to go back to the outer loop. Then this loop will be again, it will be called here. Then according to that, it will execute. So we supposed to backtrack all these things. So the top-down backtracking, this should be done it when we have the more inner loops. Then only the language will accept it. Okay, so now let us see this how does work. Then what is actually the problem in the left regression? So example of the left regression, look at here, the A producing A alpha. So again the A it can be produced A alpha, again the A can be produced A alpha, again the A can be produced and so on etc. It never ends with the alpha because the grammar rule is given or it producing that A producing A alpha. So it goes and so on, etc. till the end. So we could not reach the final input symbols what we have or the given input word. Okay, so I hope you understand what is backtracking and what is that left regression clearly. We will move on to the next one. Okay, so what is that left factoring? To eliminating the left regression, we have a rule. That rule, if you apply that rule, any left regressive grammar that could be rewritten by eliminating the left factoring. So that is the rule that we are going to show it now. So the top-down parsing method cannot handle the left recursive grammar. Please note down here, the top-down parsers cannot handle, which in the sense the parser may not work. The parser may not work when we have the left recursive grammar. So the top-down parsing may not work. So not may not, it won't work because it won't reach that the symbols what we supposed to reach. So the transformation that eliminates the left regression is needed. Of course, we need to transform the left factoring into the left regression into the left factoring. So this is consider this example when we have a statement like this. This is that rule of producing it. So when we have it, the A producing A alpha or beta. So consider this when we have a statement like this, we have to consider it. We have to split like this. So A producing that A alpha. We can read it like this also. The separate, different separate production rule also can be written like this instead of this alternate. Look at this. Instead of writing that alternate by using the bar symbol, we can write it separately. The grammar symbols like A producing A alpha or A producing the beta. Okay. So how do we eliminate that the left regression by using the left factoring? So for this, when we have a grammar like this, so the A producing the beta A dash. So we are giving that we are adding that new symbol that is A dash for the symbol A. Instead of A, we are creating one more additional symbol by using that A. That is why we are added the A dash. So this is the epsilon. This epsilon is a game changer in the grammar. Without epsilon, most of the grammar may not work properly. The epsilon is very, very powerful. It's because epsilon in the sense it's null, it's empty. So any programming language that support empty statement, in C language, if you write it any main function only with a semicolon, that will work. That will compile successfully because it's epsilon. It's an empty statement. So null statement, some of the situation, the null statement or the empty statement is powerful one. So if we don't have that epsilon, we may not reach that. Even the grammar cannot produce any words. So the epsilon is a sense we can use either to start for the particular inputs or we can use for the end up with the input symbols. For the beginning and ending also can be connected with the epsilon. That will be nice to have the grammar. Okay. So eliminating the grammars, eliminating the eliminated grammar will be like this. You can take a look at this. I erase it everything. Then you can take a look at it. The difference, how the difference is here now. Okay, so it is eliminated grammar. This is the left recursive. This is actually the given grammar. This example grammar is the left recursive grammar. After eliminating this is the rewriting rule or the eliminating the grammar like this. Okay, so how do we done this? How we have done this? Here, A is in the sense beta A dash. then the A dash is producing A dash alpha or epsilon. So this the same grammar without changing its meaning. We are adding by that A dash and then the epsilon. This is a grammar rule to eliminate the left recursive. This is called actually left factoring. I repeat that there might be a left recursive grammar. So those left recursion grammar can be eliminated by left factoring. So that left factoring is nothing but a beta a dash alpha epsilon. This is the writing rule for generating any left recursive grammar can be left factored by this rule. Okay, guys, I hope you understand this, and we'll move on to this. So, what is left recursive distant parsing? Now we will move on to actually the parsing technique, that is recursive distant parsing. Is a parsing with backtracking until to get matched with input sentence. You guys, now as we have discussed already, you can set this the puzzles game when we have that a cat wanted to find out its home, or the cat wanted to find out the milk, like that, or the rat wanted to find out that the particular place, like that. We need to have some puzzles game. So in that game, we used to have that backtracking in the sense we are finding out a way. If there is no way, then we have to go back. Then we need to find out another way to reach the destination. Okay, so a parser that uses a set of recursive procedures to recognize its input with backtracking is called the recursive descent parsing. Sorry, it's not the left recursive; it is the recursive descent parsing. In the sense, we need to backtrack until to reach the desired input string. Okay, so that's what we're going to see it now. We'll see this. A useful method for manipulating grammars into a form of suitable recursive distant parsing is left factoring. It's of course, sometimes if there is any um, left recursion, then we have to apply the left factoring so that it is easy to do that, the recursive distant parsing. Okay, so left factoring is a process of factoring out of the common prefixes or of alternatives. Okay, okay, guys. Now, the grammar, consider this grammar, the same grammar, how the left recursion is working, or the recursive descent parser is working. Let us check it out here. So the same input word CAD, consider that the S producing that CAD. Okay, first. Then now you're going to understand easily what is left recursive, or that recursive descent parser. Okay, recursive descent parser. So this parser, what does do here? Here, what happens? Look at here. The S produces CAD, and then the first alternate. When we consider the first alternate C, A, B, and D, it is not matching it. Look at here. The first input symbol is C, and then the second input symbol is A, but the third input symbol is D. But here the third input symbol is B here. So it is not matching with that. So if you are using that first alternates, when we substitute the capital A into AB, so we will get that output word will be like this: the small c, and then small a, and small b, and small d. Okay, so what we have done it here, so this AB is replaced by the non-terminal A, because we have used the first alternate of this production rule. Okay, so when we use this, we may not reach the input symbol here. Look at here, the input symbol is CAD, but we got it CABD. So what we supposed to do? Then we have to do the backtracking. So what is the backtracking? We need to go back to the alternates of the A and find out is there any other alternate to match with that input symbol. Yes, of course, look at here, the A is matching with the small a, right? So when we replace this AB, instead of AB, when we replace it small a alone, then CAD will be, we got it CAD. Finally, we got that output, or it is matched with the desired input symbol. So this is how it works. So this is the backtracking. So first we are not matching with, so second time We are looking into that second alternate. So according to the second alternate, it is matching with the input word. So the grammar is accepted the given source code or the given input word. Okay. With this, the consider the another grammar. This is actually that another grammar here. You look at here, guys. So what is the grammar here? This is actually it's a little complicated here. I'll tell you what it is. It's very simple. If you are looking into, if you are really listening this class, I'm sure that you can easily understand that. So the S produces ICTS, then ICTSCS. If you see like this, you may not understand clearly. I'll tell you what it is. A statement can be, yes, consider, yes, is a statement. So a statement can be if condition then statement. Here that I represents if, then T represents the then, because those are the keywords. The keywords cannot be changed. It's a terminal. But the non-terminal can be reproduced some other terminals. That is always you know that, right? So once again, so the statement can be if condition then statement, or the statement can be like if condition then statement, else statement, or the statement can be directly a statement, or the C can be the B here any statement. Okay, B is the um, any condition, valid condition. Okay, guys. So the left factoring, this is actually the left factoring is there because the statement can produce again and again and again the same if then else, if then else, if then else condition. It goes still. So we must use that left factoring like this. Okay, here the S is the we have to use it applied here. The left factoring this grammar is yes, I mean the if condition then statement, then the statement dash. That is yes dash is added, and then here we have to consider that the A is the beta. Okay, then according to the rule. Then the S dash is producing that ES and then else statement or epsilon. That could be whenever it comes the else statement, the else statement could be entered with that. So that's why we are using that epsilon. Okay, the S dash we have added. So the S dash can be the if statement can be end up with the else statement or epsilon. Only we can have if alone, or we can have consider the else statement. The else statement ends with epsilon. So see in the sense that is only it produces the conditions. Okay, so so this is another example that we have to do it here. With this, we are completing it. The next lecture we will see about more on this, and we will move on to the predictive parsing. Today we have seen that what is top-down parser, recursive parser, and then the left recursion elimination. How we have done the left recursion elimination, and then the leftmost derivation, and then recursive descent parser we have seen in this class. So the question answer session. Let me ask the first question. Dash can be viewed as an attempt to find the leftmost derivation. That is, yes, you are right. That is top-down parsing. Then the next question, top-down parsers build parse trees from the top, that is root to the leaves as the bottom. So this actually, what do we say this as the options are tree or the in order or pre-order tree or the post-order tree. Yes, you are right. Pre-order. It is not the in order, it is in the pre-order. It is wrong here. So the correct answer is this. The correct answer is this. This is not that correct answer. I'm sorry because it's mistake. Because the pre-order the root, then left subtree, then right subtree. That should be the order. Okay. And the third question: what is the problem with the top-down parser? A parse tree, a left recursion, or the parsing table, or input symbol? The problem is left recursion. You are right, exactly, guys. Very good. Then which is not a left recursive grammar according to this grammar? Which is not a left recursive grammar? You have to consider and look into that. And see, the left recursion you can easily understand. See that non-terminal is in left hand side, the non-terminal is right hand side. Same non-terminal is right hand side, left hand side and right hand side. So left hand side also is there and right hand side also the same non-terminal is there, but only this is not there in the right hand side. So the final answer is the final answer. Okay, so a parser that uses a set of recursive procedures to recognize its input with backtracking is called, that is, what is that backtracking is called? It is the recursive descent parsing. You are right, exactly. Thank you guys. With this, we are completing this lecture, that is top-down parsing. The next lecture, where we will see about predictive parsing. The predictive parsing is quite complicated because we have to predict it. Instead of backtracking, what we supposed to do it, we are moving to the next level. So instead of backtracking, so which is the next alternative for the specific non-terminal symbols, instead of that, we can move on to the directly that what inputs according to the input symbol, we can choose that exact alternatives. Okay, so that's what we will see in the next class. Thank you all.